My name is Tamsin. I'm Professor of Earth Sciences here at Oxford and a Fellow at Univ.
So Tamsin, can you tell me what are some of the most exciting findings to emerge from your work?
So my work largely focuses around volcanoes. When people think about volcanoes, they probably think about large explosive eruptions causing lots of destruction and sometimes death. And I do work on things relevant to that as well. But a lot of my work looks at the environmental impacts of volcanoes. And these can be both positive and negative. And my work encompasses the whole of geological time on this planet. So that's 4.5 billion years, which is quite a lot of time to play with. So lots of different exciting findings, but one that comes from during my PhD was I discovered a previously unappreciated role of volcanoes in the nitrogen cycle. So there's loads of nitrogen in Earth's atmosphere and has been for a very long time, but biology like us cannot use it in its gaseous form. It's tied up, it's inert, it's not available to us. So we need ways that nitrogen is made available to us. Nowadays, it's mainly through biology, through leguminous plants and nitrogen-fixing bacteria and such like. But back in deep time, biology wasn't doing that. So we need sources of fixed nitrogen that are abiotic, that do not involve biology. Now, lightning is a major focus, a major source of fixed nitrogen in the early Earth. But actually, one of the things I discovered is volcanic heat could do the same job and could fix nitrogen out of the atmosphere in a way that biology can use. And this could have been one of the components that helped us to develop life on this planet.
So Earth Sciences at Univ appears to sit at the intersection of planetary science, sustainability, and innovation. What role is the college playing in advancing these areas?
Well, Univ has a long history in Earth Sciences. We host one of the 3 statutory chairs, the Chair of Geology. But we've really built an incredibly vibrant community here of fellows, graduate students and undergraduates. And I think communities like that at Univ help us to bring all these different disciplines together with the inputs, of course, of the vibrancy of having undergraduate students and PhD students here as well. So it's a huge mixture of things, a huge mixture of a melting pot in terms of developing that community. And I'm really proud of the diversity that we have in our research in Earth Sciences here.
And some people might find a subject like Earth Sciences intimidating, having not really studied it at school. What would you say to them?
It's an extremely exciting subject. I didn't study it as an undergraduate, actually. I did chemistry, but I really wish I had. I think we're a really friendly department. The undergraduates in our department go off on a field trip in the first few weeks of study, and they really get to know each other. They really build a cohort. So I think it's a very friendly and supportive place to be. But of course, also, you have studied it at school because you've done physics, chemistry and biology. And studying Earth Sciences at university is really a combination of all those things with mathematics in the background there as the language that we use to understand the world around us. So if you like science and you're interested in the world around us and you're interested in understanding how it's changing and how to adapt and solve the problems that we're going to face as a species in terms of our environment in the future, I think we're a great place to come and study.
And how did you find that shift from studying chemistry in undergrad to Earth Sciences in postgrad?
I was really excited by it, but of course intimidated. There were loads of words I didn't know when I was sitting in all the seminars in my first year as a graduate student. But I'm so glad I made the change. It's a real privilege to work outside in the great outdoors on natural phenomena and apply the science that I love.
So what do you see as the urgent global challenges of today?
Oh, there are so many urgent global challenges of today. But perhaps some of the ones that my research touches on are what the planet is going to do with all the carbon that we are putting out into the atmosphere, how it's going to change in response to that, how it's ultimately going to take that carbon out of the atmosphere and recover from that. But also how we push forward using technology. So if we want to push into the green revolution and decarbonise our technologies, we're going to actually need a lot more of the Earth's resources to do that as well. So just taking, for example, battery technology, batteries require critical metals. And it is by mining these from the Earth's crust that we get these critical metals that are required for green technologies. And that's a really key area of endeavour in the earth sciences, is understanding how to source critical metals.
And how are students at the college involved in that sort of research?
Well, we're trying to think around these problems in all sorts of different ways. So one of the ways that we try and understand Earth's carbon cycle, which is what we are perturbing at the moment, or changing at the moment with our fossil fuel emissions. One of the ways that we try and understand that is by looking into Earth's past. So there are episodes in Earth's past when the carbon cycle has been very disrupted. And these are often associated with very large-scale episodes of volcanism, so my expertise. These episodes are called large igneous provinces, and essentially they kind of double the rate of volcanism on our planet for about 1 million years. And they put out lots and lots of carbon. So we can look at the way the planet reacts to that in order to inform our understanding of how the planet might react in the future. But on another strand of our research as well is thinking about different ways of getting metals out of the Earth's crust. And one really innovative way that we're championing here in Univ is thinking about how we might extract metals from brines, so from volcanic brines, which are sort of salty, hot fluids within volcanoes. So these are really useful and are used in the geothermal industry to basically give us green power or low carbon power. But we might also be able to use them as a source of metals. So this is championed by fellows like John Blundy and myself in college and others across my department and the university through a recent initiative called Oxford Earth. But underlying that is our student body. So first of all, we recruit students through the department into their fourth year research projects, which is a really rich part of our undergraduate programme where they get to be embedded in a research team and contribute to these types of research endeavours. But then also, of course, through our DPhil students who are getting really, really deep into some of these issues and publishing papers right at the cutting edge of thinking in these areas.
I imagine that this sort of work leads in quite a lot of different directions. So what sort of things have some of the students that you've worked with gone on to do?
All sorts of different things. So many of them stay in academia. You know, several of my students now are professors in their own right, and I have PhD student grandchildren and great-grandchildren, I think, now maybe, which makes me feel a little bit old. But then they go off into scientific policy work. So several of my students have gone off into the civil service, some into NGOs, non-governmental organisations, some into environmental consultancy, and then others into things unrelated to science as well, which are very valid, so law or other types of consultancy also.
Mm-hmm. And on a personal note, what motivates you to keep doing what you're doing?
I'm fascinated by the world around me and I love science. And doing what I do allows me to combine those two fascinations. I also want to solve problems. I like problems for their academic stimulation, but I also want to solve problems that are relevant to our planet and our species.
And is there anything that you could say would define a successful earth scientist?
I think earth sciences is a really broad church. So I don't think there's one way to be a successful earth scientist at all. I think what unites us is a great excitement in science and a great excitement in science about our planet and other planets as well. So enormous curiosity.
So at Univ, we use a tutorial system. In your experience, what kind of things does this teaching system unlock in students, especially in a field that's as unique and complex as earth sciences?
I think being taught through the tutorial system is an enormous privilege, although the students may not always appreciate that while they are here. As a teacher, we are really fortunate. We get very, very talented students coming into Oxford, and the tutorial system really allows us to push them and tailor their education to them as well. So in a field like earth sciences, it's really important that we teach them a whole bunch of technical knowledge. So in the tutorial system, when you've got small group teaching, there's really nowhere to hide if you're struggling, which is a good thing. I need to remind my students of this, because this allows us to sort it out and to correct their understanding and to correct their technical understanding as well. But I think the other thing that the small group teaching really unlocks is teaching them to think, and teaching them to think for themselves, and teaching them to justify their opinions and to use evidence to justify their opinions. And really, as I say, in a small group, there's nowhere to hide. So you need to be able to defend your position and back it up. And that is such an important skill in this world that we live in.
So looking ahead, what opportunities or challenges do you think earth sciences will face in the next 10 to 20 years? And what role do you hope Univ will place in addressing those?
There are so many challenges we're going to face as humanity in the coming years. I think within the earth sciences, we have a real role to play in terms of thinking about how to sustainably exploit Earth's natural resources. So, as I mentioned earlier, thinking about critical metals and how to extract critical metals from Earth's crust without destroying sacred mountains, destroying the landscapes that we love as well. So I think that will be something that Earth sciences can really contribute to. We've done a lot over the last few decades in Earth sciences about defining the problems we're going to face. And I think this role going forward really is repositioning ourselves to take those same critical skills and think about how we move that into solution space in terms of solutioneering. So one set of solutions, as I said, is about critical metals as well, but I think also the interdisciplinary nature of the subject is going to be really key. So in my area of volcanology, for example, we can get better and better at predicting when volcanic eruptions are going to happen. But we also need to think about how we communicate with communities and how we communicate those hazards and how we help people to manage their lives and livelihoods around that. And I think that's where the interdisciplinarity that a subject like earth sciences really lends itself to, which has a real sense of place as well as science, really come into play. And if I fold back onto the critical metals discussion, that will be really important there too, because if we want to extract resources from Earth's crust, we need to do that with the communities that are local to those places as well, and with their consent and with the right social license. So pulling all these threads together, I think, is one of the key challenges in the coming decades. And this will apply to a whole range of different things, but I think earth sciences, with its very interdisciplinary nature and its really strong sense of the planet and place, will be really, really well positioned to do good in this area.
Tamsin, what drew you to volcanology?
So actually, I'm an accidental volcanologist. Many of my colleagues have been obsessed by volcanoes since they were children, and then have made this into a profession. And I'm certainly interested by them, but it wasn't something that persisted. Actually, astronomy was what really pulled me into science. I was fascinated by the stars and planets, and knew loads and loads about that when I was an inquisitive 8-year-old. When I did my chemistry degree, I had a couple of years out of science, and I decided I wanted to go back into science, but I didn't want to be in the lab all the time. I loved lab work, but I wanted to do something that was larger scale and about the world around us. So I was looking at different PhDs and nearly did one in ocean chemistry, because I'm very keen on the sea and sailing. And I was looking through second choice projects in the physical booklet, as it was then, before the internet was big time, and spotted this one on the atmospheric chemistry of volcanic activity or volcanic plumes. And actually, I'd done a specialist module in atmospheric chemistry in my chemistry degree. So I thought I could do that. And then when I got to the interview stage and I met Clive, who was to become my PhD supervisor, I just got super inspired by it. And I could see some things I could really contribute and some things that I could do a bit differently. So I got hooked, and I got hooked on volcanoes, and the rest, as they say, is history.
And most people see volcanoes as these big, scary, ominous things. What's so good about them? How do they help our planet?
Well, I'll come on to that in a second, but I think when you spend time around volcanoes, they are big, they can be very scary, and people certainly, there have been some really, really tragic crises associated with volcanic eruptions. But actually, people who live around volcanoes often revere them as well, and in some cases worship them as gods or goddesses. So we have a complex relationship with these amazing places and these amazing mountains. And it's not quite as simple even as saying that the people who live around them just fear them. The people who live around them also recognise how they create land. In the case of volcanoes like Kilauea in Hawaii, it builds new land where lava flows pour into the sea. Or in places like Etna and Sicily, where the mountain creates its own weather, so you get higher rainfall in the area of Sicily there, so it's more fertile. Also, the scattering of ash onto the soils keeps them very fertile as well, with new nutrients as well. So we have a complex relationship with volcanoes, even in the local sense. On a planetary scale, and this is actually sort of one of the things that really fascinates me about them. So we see them as a threat, but actually I would argue we wouldn't be here if it wasn't for volcanic activity. Volcanic activity over long time periods sustains our atmosphere, so it keeps it it keeps it sufficient density, it keeps the right things in it to keep life sustained on the planet. And over very long time periods as well, volcanoes are part of an amazing system of checks and balances on our planet that have kept the climate relatively stable over very long geological periods of history. So really, volcanoes give us life as well as meting out death and destruction. And this sort of dual personality that they have is one of the things that really fascinates me about them.
And your work must have taken you to some amazing places around the world. Are there any highlights from your career thus far?
Oh, so many. So many. I mean, I mentioned Etna. Etna on Sicily is a very special place to work. I have some really wonderful colleagues who I work on that volcano with. Sicily is an incredible island as well. I think Etna's every time I go up Etna, it's changed. So it's always bits of it are falling away, new cones will build up, its personality shifts all the time, but it's an incredibly beautiful place. It's also the only place, I think the food and the wine are so good on Sicily, I think it's pretty much the only place I've put on weight having gone to do field work as well.
So are there any findings or discoveries from your field that might shock people?
I don't know about shock, but something really cool we were working on the other day, me and John Blundy actually. So some of the work I did for my PhD looked at how much metals volcanoes put out in their fumes, in the gases that they emit in places like Etna and Sicily. So we were doing a scaling up exercise, working out if we added up all the volcanoes around the world every year, how much of different metals they put out. And actually we found that for some metals like copper, lithium, silver and gold, volcanoes possibly put out more of these metals every year than similar amount or more than we mine out of Earth's crust. And I thought that was a really cool finding, and it really illustrates the potential for me of thinking creatively about how we might get more metals out of geothermal brines within volcanoes, for example.
And is there a way to extract the metals from those gases?
Not really, because they're so dilute by the time they get out, and also building an enormous umbrella over an active volcano is
tricky.
It's firstly tricky, and it's probably not going to last very long. Mm-hmm. These are very extreme environments. They tend to throw out sharp, pointy rocks, and also they're very acidic. So any sort of infrastructure can easily get very corroded. So no, this is where the idea of drilling into active volcanic systems in the way that we do for geothermal power extraction already. So drilling in and then harvesting the bounty, the metallic bounty from those fluids when you're circulating them through to extract heat as well. That's where that idea comes from, rather than building some enormous volcano capture system.
And you mentioned there that there are extreme locations that you're going to. Are there any risks involved with your work?
Yes, of course, and unfortunately every now and again volcanologists do get killed in the line of duty. We take that extremely seriously. Every time I take new students to a volcano, I make it incredibly clear that no measurement is worth risking your life for, that this is not an adrenaline sport, it is a science. We always work with the local monitoring teams to understand what the state of the volcano is. We always try and only work on volcanoes if they're in a relatively safe state. But they are unpredictable, and you do have to realise, as anybody visiting an active volcano needs to realise, that they can do unexpected things.
So Tamsin, in the face of today's challenges like global warming, what gives you hope?
Hope is so important. I think humanity is very good at solving problems once they are right up in our faces. And I think that gives me a lot of hope. There are lots of people who want to solve the problems that we're creating. That also gives me hope. And I guess also the geological timescale gives me some hope as well, which might sound a bit strange. But, this planet is very, very old, and we are a very recent phenomenon on it. So if I stretch my arm out, and this is 4.5 billion years, the birth of the planet here, and my fingertips are now here, sitting in Univ. Actually, humans have only been on, if I took a nail file and just drew a nail file across my fingernails there, that's how long humans have been on the face of the Earth. So we really are the nail dust of the geological timescale. So we are really changing things at the moment. We really are a geological force in terms of the amount of carbon that we're putting out. But the planet has dealt with large quantities of carbon before, and over hundreds of thousands to millions of years, it will deal with the carbon we're putting out now and lock it back into different reserves in the Earth. So the planet will be okay. It's just what role we play in the future of our planet, and that's really the decision that we're making as a species. So our own future is in our hands, but the planet, I think, will be okay in the long run, and life, in the broader sense, will persist.
How does the planet lock those carbon?
So there's a balance to so if we look back in geological time, when we have periods where volcanoes have put out huge quantities of carbon, so these large igneous provinces many millions of years ago, over time the carbon is slowly dissolved in rainwater and then reacted with surface rocks and taken down into the oceans and then sequestered, sometimes by biology in terms of shells, and then built into carbonate rocks ultimately. So then that locks it away out of the atmosphere. So the Earth has a long-term thermostat actually inbuilt that kind of balances out carbon emissions. If the temperature goes up, the rate of weathering increases and pulls carbon out of the atmosphere, and conversely, if it cools down, carbon dioxide can build up in the atmosphere. So it keeps the temperatures within a certain range of bounds. So over the long-term history of the planet, there are these checks and balances. But we're just doing things very, very, very much more quickly than the planet can deal with in terms of our emission rates. So it's not something that's going to sort out what we're doing and our short-term future, but it is something that will sort out Earth's long-term future.
So it's like the planet has its own greater plan.
Well, that's one way of looking at it.
Thank you so much for joining us today. It was fascinating to hear about your work and your life.
No problem. Great to chat to you.